Then we'll continue now with Fransisco Park from South Korea.
Thank you. Should I start? Okay, so hello everyone. My name is Fransisco Park, and I'm from South Korea. I'm going to talk about dark matter axion search using 18 Tesla superconducting magnet today. So yes, all of this looks quite complicated. So let's get right into it. So we have a strong CP problem in the modern theory of quantum physics called quantum chromodynamics. But the basics are quite simple. So you see that the modern theory, the quantum chromodynamics, is made to violate some kind of symmetries in the nature. So it actually violates the charge parity symmetry, but this, in fact, means that it violates a time symmetry. So what does this mean? So assume that you have a clockwise current. Then you have a magnetic field heading to the top. But if you reverse time here, it'll reverse the direction and the magnetic field also. But for electric fields, this doesn't work. Even if you reverse time, it's the same. So what is the result of this time reversal symmetry breaking is that you get a non-zero neutron electric dipole moment. But what happens if you go and actually measure one? You get 0. So this is a problem called the strong CP problem. And the axion is a hypothetical particle which can solve this problem. And it was also discovered theoretically that axions has minimal interactions with any other matter we know. So this means that it can be a dark matter. It's a dark matter candidate. So how are we going to look for these axions? So we have a transition of axions to 2 microwave photons. It's very weak, but we do have. So how are we going to see this very weak photons? So we have a copper cavity here. So we are going to see these microwave photons using the normal modes of this tunable cavity. So it's nothing else than just a copper can, but which we can tune the effective diameter to tune the normal frequency of it. So we can calculate the frequency sweep rate, which means that how many axions frequencies we can test for unit time. We see that the magnetic field is actually very important. We see the power of 4. So this is why we employ the 18 Tesla, which is almost a world record of a stable magnet. So we see the frequency sweep rate like this. Okay. And then what is also needed is that there's so much noise compared to the very, very weak signal, so that we need to average over a whole bunch of data. So what should we do is that we need to make sure that our machine does not actually lose any data at all. So how can we do that? We gave random inputs to the machine, and we checked that if they match actually the outputs we have measured. So, and then also, this tremendous amount of data needs to be turned into the frequency domain to see actually where we have our particles, this wanted axion particle. So also a multi-core Fourier transform using many computers has been developed to optimally save the data we are looking in from the copper rod. So here are the final results. So these are the spectrums we have measured from our copper cavity. And then on the right, you see the exclusion plot. So the KSZV is the limit, the theoretical power of the axion. And the confidence level 95% graph that we have removed, we're sure that there is no axion in that region. So this is how the dark matter search continues. And we see that we have still a whole bunch. We are the purple experiment there. We still need to see all those frequencies to completely say the axion does not exist, or if it exists at some frequency if we find it. So this was my project. Thank you very much.
Thank you very much. Okay, do we have a question? Yes, there is one question.
Hi, you say that
Yes.
Electrical fields,
Yes.
when you reverse time, they don't reverse.
Yes, yes.
How can you know that?
Oh, okay. So actually, to be very rigorous, you should go into the series, this actual quantum chromodynamics and see its structure. But we have a very analogy using only simple classical mechanics physics. So you know that if you have a clockwise current, we have a magnetic field going upwards. But if we change time, the current will change direction, and also the magnetic field. But for electric fields, they are naturally generated by, for example, charges. So assume a plus charge here and a minus charge here. Then you'll have an electric field heading from the top to the bottom. But even if you change time, it's the same. They're still there, so the electric field will be about the same. But instead, think about the parity, which changes the space. In this case, these two locations are changed, so the electric field is changed. And in this case, actually, the magnetic field stays constant.
Okay.
Thank you.
Is there any other question? Yes, there's one question down here. Maybe also to encourage you to ask questions. It doesn't necessarily need to be always about content. You can also ask, what is your motivation? How did you come to this research? So yeah, all kind of questions are welcome.
Yeah, thank you for talk. You showed in some of the earlier slides that dark matter is something like 25% of the energy content of the universe.
Yes.
So the axion particle, how large part of that dark matter slice would that be, do you think?
Yes. Oh, thank you. Yes, for the question. So actually, that is actually research we should do. So when we see the peak, so we will have the estimated dark matter density in our universe, but the signal coming out from the detector will depend on this density. So maybe some of dark matter is made of axions, maybe none, or maybe more, maybe only half of them would be axions. So this will actually be analyzed if we actually see an axion peak and we discover it. So yes, it could be all of it. It could be a very small portion of it.
Yeah, thank you.
Thank you.
Is there any other question? Okay, then thank you very much.
Thank you very much.
Thank you. You can go over there. Okay.